Okay, hope it is visible also. Okay. Okay, so last class what we have seen is actually maybe the probability, maybe the basics of probabilities, maybe the sum rule and the product rule. And then we have seen few results, okay, few basic definitions of maybe probabilities, and maybe few terminologies like a prior probability, posterior probability, etc. Okay, so today we will continue the same discussion on probabilities. So today what we will be concentrating on, maybe on the first part, we will be concentrating on maybe the probability density functions or probability distributions generally. Okay, so the probability distributions, so that can be for maybe for both maybe discrete variables as well as for maybe say continuous variables. uh, so we will first we have already actually whatever we have discussed is actually for probability discrete sorry, for the discrete random variables. So we have seen that in the last class. So today we will discuss about the continuous variables. Okay, so here so we have actually probability density is usually actually probability with respect to continuous variables. Okay, so that means we are assuming that so the x is actually a real valued variable. Okay, x is a real valued variable. Okay, and then so if you consider real valued variable, we know that it can take any value. Okay, so that means if you make a very small maybe addition of maybe very small quantity, we will get a new real value. Okay, so that means we have actually infinite maybe values in between. Okay, if you consider any two values in the case of a real valued variable. So in that context, suppose we are having say the probability of suppose we consider probability of x, okay, falling in the interval x comma x plus delta x. Okay, so that means we consider a very small interval. So and we are assuming that delta x is actually tends to 0, so that means very small change. Okay, assume that that probability okay of that particular falling in the range is actually defined as probability of x into delta of x. Okay, then we say that a p of x, so this p of x is actually called a probability density over x. So that is actually the definition of probability density, or sometimes called okay, probability density function, or pdf. Okay, so that is a basic definition. So we have a real value and we are actually considering a very small interval. Okay, and then we are assuming that the probability that the variable x actually falls in that interval is actually p of x into delta of x. Okay, delta x, then we call p of x as the probability density over x. So that is a basic definition. And suppose if you consider say two say values, say for example a and b, range of values. So that means assume that we are having x lies in the interval a comma b. Okay, so maybe two real numbers. So in that case, what is going to be the probability is actually how we will calculate the probability is actually probability of x element of a comma b. Okay, so that is actually nothing but the integral over a to b px into dx. So that is a it is actually or actually maybe summing it over, integrating over the range of say a and b. So that is going to be the probability that x lies in the interval a comma b. So these are basic definitions. We will be using maybe, or maybe they will be referring to these type of definitions maybe when we discuss later maybe say concepts in pattern recognition. And similar to what maybe as these are probabilities, similar to what we have discussed for the discrete variables, p of x, okay, it must satisfy that p of x greater than or equal to 0, and the total. Okay, so for example, if you are actually plotting, okay, a probability distribution, then maybe the area under that curve, or maybe integral from minus infinity to plus infinity, p of x into d of x must be 1. So these two must be say satisfied. Okay, so that is another say two results that we can maybe write in. And there is another so there is a possibility that we will be having a problem where only discrete values. Okay, all the variables involved or all the features involved are actually say discrete in form, and there can be situations that what continuous, okay, alone cases. That means all the features or all the variables under considerations are continuous, or there's a chance that okay, in real situations we'll have a mixture of maybe discrete as well as random variables. So there is another probability distribution similar to what we have seen, like a cumulative distribution function. Okay, probability distribution function, which is actually maybe suited for maybe when we use a mixture of maybe random but continuous as well as discrete variables. So we will be discussing that later, but the definition is we are actually considering x lies in the interval maybe minus infinity to a particular value z. Okay, so that's a capital P. So it's a cumulative function. That's we are having a separate notation. So that is actually defined as probability of z is equal to, okay, minus infinity to z, okay, p of x into, okay, dx. So that is a definition for that particular cumulative distribution function. Okay, and so we have actually maybe say for example, if you look into this particular plot, here we have the p of x actually represents it. Okay, the p of x actually represents the cumulative function, and generally px, so that is actually our probability distribution function for the variable x. So that is generally considered as an we'll get okay, individual probability values by taking a derivative of maybe the cumulative probability distribution function. So that is a that we will see later. Okay, we'll discuss maybe in detail maybe whenever it is required, but you keep in mind that there is one more probability distribution function, the cumulative distribution function, and maybe so here so this is the result. So that means, okay, dash is actually used to represent the derivative. So that means at a particular point, then if you are actually, okay, finding out the derivative, then that will result in the that particular probability value, okay, or the say we'll get the p of x, okay, value at that particular point. So that is actually maybe maybe the case of cumulative probability distribution. So that is actually about maybe two. One is a probability density function, okay, and maybe usually cumulative distribution function. Okay, so CDF and VDF. Okay, I think this is maybe the concepts are easy to understand. And now we will go to the next slide. Okay, so okay, so now we will see. Suppose we are having so far what we have discussed is actually we considered only one random variables. Okay, in the probability, okay, definition, that is p of x. Okay, so but usually in pattern recognition problems we need actually continuous, okay, random variables, and that is several, okay, in number. So in such cases, assume that we are having x1, x2, x3, etc. up to xd. Say for example, we are having a feature vector, okay, that is of say d dimension, where each of them are actually we consider as a random variable. So that means you will have x1, x2, etc. up to xd, say d dimensional data. Then so in that case, we'll have a vector x. Okay, so that means we'll have actually a vector of maybe x1, okay, x2, etc. Okay, and xd. Okay, so we'll have a vector x actually. So that is actually this particular vector. Then we can actually define, okay, a joint probability density for such a vector also. So that means when you are having multiple say continuous variables. So in that case, we have it is p of x, which is nothing but the probability of x1 comma x2 comma xd, such that okay. So what is the meaning of this one is actually so it is actually the probability of the vector x. Okay, you have to imagine that you have to imagine a d-dimensional space. Okay, so and maybe a vector. So when you consider one data point, it will have maybe a set of values from f corresponding to x1, x2, etc., etc. up to xd. Okay, so that is the picture that should come into your mind. A d-dimensional space. Okay. Okay, so then now what we are looking is what is the probability of a given vector x, okay, falling in an infinitesimal small volume of delta x. Okay, so here we are actually considering a small volume of X because it's a d-dimensional space. Okay, and that containing a particular point because we have a okay. This particular point will be falling in a particular, say we are considering in a volume of maybe say case, and so that the point actually falling in that particular say small volume is actually p into delta x. So you can see that the definitions are exactly same. The only thing is actually the small variable x is actually replaced with the vector, okay, x. Okay, so that is only so that the point is that whatever we derive, okay, we define it for a single random variable, okay, continuous case can be extended to multiple say variables or even a vector, okay, x. So that is a point. So that means in that case we have actually, okay, p of x, okay, greater than or equal to 0, and maybe we have an integral of p of x into dx is equal to 1. So that is maybe it is we are actually integrating over the whole x space. Okay, so that is the difference here. Okay, so in the previous case we were actually discussing about maybe the x takes say a single range of values, maybe a to b, okay, or from minus infinity to plus infinity. But here you are actually have to integrate over the entire say x space because they are actually the space in which we are actually talking about. Okay, so that is the idea. So that means we can consider the joint probability, okay, distributions over a combination of discrete and continuous variables also. So that is a so these results are actually extendable to, okay, those cases also. Okay, so that is one point we have to keep in mind because generally we may be we our data, okay, so that's a pattern recognition problems will be encountered with such maybe say data, okay, where we'll have a combinations of discrete as well as random say maybe variables or maybe say features are actually presented. Okay, and in particular, I mean, suppose if x is a discrete random variable, okay, that was a case that we have already discussed. Then this px, okay, that's the probability of x is usually, or the probability distribution, okay, is generally called a probability mass function. Okay, so for a continuous variable, we have a probability density function, and for a discrete variable, the terminology is probability mass function. So why? So maybe the probability mass function is, so we know that whenever it is a discrete random variable, we will not have a x actually does not take all the possible values. Okay, so all the real values are not taken. So only at some intervals or at some points only the values of x are actually defined. So that means we can say that we are actually having a set of probability masses, okay, concentrated at the allowed values of x. Okay, so that is we are actually just taking, okay, maybe only those probability cases at the defined values of maybe x. So that is actually the difference. In other cases we have to sum it over for all the values. So that is a probability density function and probability mass function. Okay, maybe but the notations are also, in one case it is going to be summation and maybe in another case it is going to be the integral. Okay, but the results are actually maybe same. Okay, so they are actually applicable in maybe in both the scenarios. Okay, so that is a another point. Okay, so here also we have the sum and product rules applicable. Okay, so similar to what we have actually seen in the discrete cases. So that means we have the p of x, maybe something like a marginal probability or whatever we have okay, called a sum rule. So here in the sum is actually maybe the integral over p x y comma into dy. Okay, so here we are actually finding out okay, for x. Okay, so that's why we are actually integrating with respect to, okay, so that so dy. Okay, and similarly p of xy is actually defined as, okay, probability of y given x into probability of x. Okay, so that is a same rule that we have seen. Okay, and but that is applicable in this case also. Okay, so that's a sum and product rules in this case. So that is actually generally about a probability distribution function. Okay, sorry, probability distributions about in the form of PDF and a PMF. And now we will go to maybe another maybe case where these probabilities are actually used for, okay, maybe defining, okay, some of the say values, okay, of a function, of a given function. So one such thing is actually the expectations, okay, of a function, okay, expectation of a function. So the word expectation actually refers to, okay, maybe see the how much you are actually expecting something, what you are expecting. So that means what is the expected value of a particular function, maybe. Okay, so that means something like, and you can say that it can be an average value, okay, because average value is generally considered as a value that you can always say that okay, this can be a very closer value to maybe the real value, but that is a significance of average value. So similarly, we are actually defining the expectation, okay. So that means suppose we have to find out a weighted average of a given function, okay. So there may be some situations where we have to find out the average value functions and that in a weighted fashion, okay. So in such scenarios, okay, in such scenarios, we are actually going to find out the average value of, okay, some function, okay, f of x, and under a probability distribution, okay. So that is actually what we are actually trying to look, okay. So in that case, okay, so we say that probability of x is actually called the expectation, okay, sorry, okay, sorry. So the average value of some function, okay, f of x under the probability distribution p of x is actually called the expectation of f of x. Okay, so that is a definition. Okay, maybe in verbal form, that is what is expectation of f of x. So average value, as I just mentioned. Okay, but it is actually under a probability distribution p of x, and this is a notation that is actually usually used for expectation, okay. So that is the expected value of f, okay. And now we will see that how that is actually defined for a discrete distribution as well as for a continuous distribution, okay. Okay, so for a discrete distribution, okay, again it is, we know that it is going to be a summation, okay. So that means say expected value of f is actually defined as, okay, sigma, okay, x into p of x into f of x, okay. So that is a definition for discrete distribution, okay. So that here you can see that f of x is actually multiplied with the probability value, okay. So that means and we are actually taking a summation over the entire x, okay. So that is a case. So that means the average is actually weighted by the, okay, so that is a weighting that we have maybe seen earlier, and it is actually by the relative probabilities of the different values of x, okay. So if you are given, say for example, three values, okay, for a x, then you have to find out the probability values, okay, and the function values, and multiply and take the summation. So that is a way we can actually find out the expected value, okay, for a discrete distribution, okay. So that is a case, and now the same thing can be extended to continuous variables also, okay. But only the difference is, instead of our say, summation, it is integral p of x into, okay, f of x into dx. So there we are actually integrating over the all the possible values, okay, maybe wherever you are considering the whole interval, or maybe a to b or whatever it is. So that is a expected value, okay, for a continuous variable. So I think so this results, okay, we will be making we will be using, okay, at many places, maybe the expected values when we discuss maybe classification techniques later, okay. So we'll see. Okay, suppose we take a, okay, either case. So that means either it is going to be a discrete or it is a maybe say continuous. Suppose we are given a finite number of endpoints. Okay, so okay, suppose we are given a that is actually drawn from, maybe sampled from maybe the probability distribution. Okay, so you don't need to bother about all other cases because you're given endpoints. So you have to consider only that endpoints, whether that is coming from what, a continuous distribution or from maybe discrete distribution does not make any difference. So in such cases, suppose, but you are actually asked to find out the expected value of f in such scenario. This is a definition, maybe a notation. So we have e of f. So it is approximately okay because this is a sampled value only. Okay, because you cannot actually say that that is the overall expectation, because this expectation you are actually defining with respect to the finite number of endpoints that is given. Because this is very important in our case, because you can see that we started with curve fitting example. Okay, so the curve fitting example, our original function was actually a sine 2 pi x function. So you can see that the sine 2 pi x actually can have a maybe infinite number of say values, or maybe okay a very large number of values. Okay, in theory, maybe if you consider all the possible say x values, but for maybe in real situations we cannot actually consider all such possibilities. So we have actually considered only 10 points. So that is a n points, the n that is actually given in our example. Okay, in the example that we have discussed about curve fitting. So in such cases, maybe you don't need to bother about maybe whether it is sampled from a continuous or from a discrete, but you can apply this particular equation 1 by n into sigma. So maybe the average function, the average value that we calculate. Okay, 1 by n into sigma n is equal to 1 to n. Okay, f of x n. Okay, so that is a this is going to be a very maybe result. This is going to be a result that will be widely used, or maybe very commonly used maybe in pattern recognition problems, because we will be given with only a finite set number of maybe data points. Okay, as in the form of training set or in the form of test set. Okay, so that is the significance of this result. So it's a finite sum over the endpoints. Okay, so that also we have to keep in mind. And so then now we will see we can always extend whatever we have discussed on expectations to maybe several variables also, but we are not going to the analysis or in detailed discussion. But you can see that suppose you come across with some notations, okay, then it should not maybe make a confusion, or it should be clear what is actually that particular term actually maybe describes. So again, we are actually defining the expectation value of f, but the difference is here we have it is on two variables x and y. Okay, and usually we are actually can say that we are taking an average over a particular say variable. Okay, when we define expectation. Okay, so that means you can mention which variable you are actually going is being averaged, that you can actually mention here. So that means we are averaging it over the distribution of x here. Okay, so that means it will be going to be p of x into f of xy. So because we are actually some averaging it over the random variable x. Okay, so that means here the 2 points with respect to this maybe term is it is with respect to distribution of x. Okay, and we know that this is going to contain a function of y also. Okay, because we are not summing it or maybe averaging the value of y. So that means it can contain maybe the y maybe variables. Okay, also. So that is a point with respect to expectations of functions of several variables. It is possible to extend it. Okay. Similarly, as a final maybe result, we can always define a conditional expectation also. Okay. Some of these will not be utilizing, but as a general discussion on these fundamentals, we will just define this one. So suppose we are to define a conditional expectation, and that is with respect to a conditional distribution. Okay, so it is also we can easily understand it. Okay, from this maybe expression. So that is again it is an expectation. Okay, of f. Okay, and the condition is actually it is given by. Okay, so in such cases, we can say that that is summation over maybe say the x probability of x given y, because y is actually is a condition already, it's a distribution given. So that means probability of x given y into f of x. So that is a way we can actually define a conditional expectation of f of x, okay, of f of x with respect to the conditional distribution. Okay, here the conditional distribution is actually the maybe the x given y, because y is already given. So what is the probability okay in this case, and we make use of that probability in order to maybe define the expectation of maybe f with respect to y. So similarly, we can write for maybe f with respect to x also, or maybe for other cases also. Maybe you can have a f with respect to maybe x, y, all these. Maybe if you are having multiple variables, okay. So that can be always be extended. So that is another maybe term. And now we will go to maybe another result, or another maybe term that will come across many times in our discussion is actually variance of a function. Okay, that is variance of f of x. Okay, I think you studied about variance. Okay, standard deviation, variance. Okay, mean, median, mode, etc. Those statistical measures you already know. So in this particular case, we will see what is the variance of f of x, maybe with respect to the expected value. Okay, in terms of expectation, how we can actually express maybe variance. So here, by definition, you can say that the variance of f, okay, the function f is actually, because we have already seen the average value or the expected value. So then what is the variance is, it is nothing but, okay, expected value of f of x, okay, minus f of x square, okay, expected value of f of x square. Okay, so that is something like x minus x bar. Okay, so like that we have a f of x into expected value of f of x is the average value. Okay, so that is actually the basic definition of variance. Okay, so that means it actually measures how much variability is there is in f of x around its mean value e of f of x, that is expected value of f of x. So I think the definition or maybe the basic concepts remains the same, but the notations are different, and how maybe the average value is actually maybe replaced with okay, maybe the expected value. That is the only difference that is actually coming here. So that is the case. And so we can actually expand the previous equation, and maybe we can write it in terms of, okay, expected value of f of x square and expected value of f of x the whole square. So it's another maybe byproduct of maybe expanding this particular equation one. Okay, because it is okay, f of x minus f of e of f of x is the whole square. So that means you can expand that, okay, to a minus b the whole square form, and you can rearrange so that you will get okay, maybe this particular maybe say in this particular form. Okay, so that is a variance. Sorry. And sometimes we may have to see what is the variance of a variable x with itself. Oh, okay, with the variable x with itself. So in such cases it is variable. Okay, so far we have defined for a function, but variable of x is actually, okay, the same, okay, definition. Yeah, that is with respect to this equation, e of x square minus, okay, e of x the whole square. Okay, so that is a when we are having a single variable. Okay, and suppose we are having a two random variables. Okay, so that is x and y. Suppose we are having two random variables x and y. Okay, then there is a another maybe measure called covariance. Okay, which is also very widely, or maybe is used. It's a very crucial measure. Okay, critical measure that has got a lot of significance in pattern recognition problems, which is a covariance. How covary x and y? So that is a covariance of x comma y. So it's a definition is actually it is nothing but x minus expected value of x into, okay, y minus expected value of y, okay, and its expectation, or the okay, average value. So that is a definition. Okay, x minus x bar into y minus y bar form. So x minus expected value of x into y minus y bar form. So this can be actually maybe maybe so this can be maybe we can rearrange, okay, by expanding this one you will get a, okay, expected value of x into y minus expectation of x into expectation of y. So that is a covariance. Okay, so this has got a lot of significance, because this actually represents the extent to which okay, x and y actually vary together. So whether they are actually independent or dependent, okay, okay, or is it a positive, positively they are actually varying or negatively varying. Okay, all these are actually very interesting for or useful for the pattern recognition analysis. So if an x and y are actually independent, okay, then we can say that it is their covariance will vanish. Okay, so there are a lot of other say results like that, or maybe that we will see later. So anyway, that is the significance of covariance. Okay, so that is a another point. Okay. Then finally, suppose we are having a two vectors. Okay. Suppose from variables. Okay. Suppose we move to vector. Okay. Two vectors, because usually pattern recognition problems, the input okay, or the data will be presented in the form of vectors. Okay. So suppose we are having two vectors of random variables x and y. Okay. So we are having two vectors. Okay. Two vectors corresponding to the random variables x and y. So in such cases, we can maybe define the covariance of okay x comma y, okay, which are represented in the form of vectors. So the definition is actually remains the same. Okay, so that is we have a e of okay x y, that is which is nothing but okay, we have the previous definition itself, that is x minus expected value of x, okay, into y minus. But here, as these are actually matrices, okay, because it's going to be covariance is going to be matrix, okay, and maybe in the form of vectors. Instead of y, we had to take a y transpose. Okay, so that is why y transpose is given, because it's a multiplication. Okay, so that is y transpose minus expected value of y transpose. So this expression is actually exactly same as the one that we have seen earlier, but the difference is instead of x, small x and y, instead of variables, we are having maybe matrices or vectors. Okay, here. So that is a maybe an extended result. Okay, for the case of vectors, because usually we will be seeing vectors maybe in our further discussions. And maybe you can maybe a specific case is actually maybe the covariance of maybe the components of a vector x with each other. So that means covariance of x is actually covariance of x with respect to x. So that is also possible. Okay, because we will be calculating this covariance matrix. Okay, and then we will be looking at the property of the covariance matrix, and then based on that we'll be defining specific cases, and analysis will be done. So that's why we define the covariance okay of vectors or covariance matrix. Okay, and so that is actually about that particular thing. I think yeah, I think with that we will finish today's discussions. Okay, so thank you for listening, and we will continue with maybe another topic, okay, related to maybe the probability in the next class. Okay, thank you for listening.
Thank you, sir.
Yeah, thank you all.